Hello and welcome everyone to our webinar, Superconductor Simulations in the Cloud. My name is Jukka Knutinen and I'm the head of marketing at Quansigned, where we have a cloud-based FEM multiphysics simulation software called Quansigned Allsolve, which we'll use for today's demonstrations. Before going any further, I'd like to inform you that this session is being recorded and we'll be sharing the recording as well as an executive summary PDF with all of the registrants after the event. So to begin, let's quickly go over our agenda for today. In the first few minutes, so very soon, we'll go over the motivation for this webinar, after which Dr. Mika Lyly, one of our senior solution specialists and one of the two technical speakers of today, will take over and guide you, first of all, through a more in-depth look at the issues faced in superconductor simulations and the ways cloud computing, namely through Quansigned Allsolve, can address these limitations. As our first demonstration, we'll see the overview and simulation setup for the 3D nuclear stellarator simulation and initiate it here live. After that, we'll see a demonstration from our other technical speaker of today, Dr. Ruuskanen, who will take us through a non-insulated 3D HTS coil simulation with magnetoquasistatics and heat transfer. He'll cover everything from creating the geometry and mesh, setting material properties, H5 formulation and heat transfer, current sources and circuit coupling, all the way to the simulation and post-processing. The other demonstration from Dr. Ruuskanen will be of superconductor filaments embedded in a copper matrix with a similar problem setup as with the non-insulated HTS coil demo. After that, we'll cover some of the other benefits provided by cloud computing, as well as address some security concerns before moving to see the results of the stellarator simulation. Finally, we'll have plenty of time for the Q&A session in the end, where you can freely ask any questions related to the topic, so be sure to stick around for that. If that sounds good to everyone, well, without further ado, let's go over why exactly we're here today and what we're actually trying to achieve. So many of you as engineers dealing with superconductor simulations might have encountered some of the issues that arise from the limited computational capabilities of desktop-based simulations, namely long run times of days or even weeks and complex simulation setups. For these problems and many others, as we will see later, but these being the biggest, utilizing distributed memory and computation, such as with an intuitive cloud-based simulation tool like Quansigned Allsolve, can provide not only a simpler setup and more accurate models and therefore results, but doing this much, much faster. How would it be like to have access to more than 32 terabytes of RAM from a laptop? How many iterations more could you do when the simulation runtime is no longer weeks, but mere hours, even minutes? How many iterations would you even have to do when you don't have to make compromises with your models and can compute much larger models with more accurate results? How would this then expedite your design and R&D processes as a whole? Well, I'll pass the microphone to my colleague Mika, who will show you what solving a simulation with hundreds of millions of unknowns looks like and how a simulation like that can be solved in a matter of minutes, again from a laptop in the browser. Thanks for joining us today, and we hope you find this webinar at the very least informative, but hopefully even eye-opening. Go ahead, Mika.
Thank you, Jukka. My name is Mika Lyly, and my background is in electromagnetics, especially superconductors. And I did my PhD at 2015 at Tampere University. And at the moment, I'm working at Quansigned as a senior solution specialist. So let's go to the slides. I will first highlight some challenges we can tackle by using Quansigned Allsolve. First challenge related to large simulations. For example, plus 15 million unknowns and even several hundreds of millions of unknowns. This is such a problem already that you cannot easily solve without a very powerful machine or access to cluster. And with Allsolve, you can use a browser for that. And these kind of problems you can face typically in case you have a very big geometry. Naturally, you cannot exploit any symmetries, or you want to do a mesh sensitivity analysis for certain geometries, then you may easily end up with very large scale simulations. As well, if you have a high aspect ratio between different objects in the geometry. The next challenge is the time-consuming transient simulations. For example, if you have nonlinear materials and complex geometry, the transient simulation may easily take days or even weeks or even longer, depending the detail of the geometry. Third, if you need to do big parametric sweeps, for example, for training AI algorithms or optimization. And typically, if one uses evolutionary algorithm-based optimization, for example, genetic algorithm or gray wolf optimization, in that case, one typically generates or initializes a population of hundreds of different geometries with different parameters. And during the optimization, new populations will be generated. So in this kind of situation, overall simulations may be easily over 1,000 simulations to really run a proper optimization. And now, due to that, typically one needs to limit the simulation time to some tens of minutes to have really a practical simulation run. But now with Allsolve, we have cloud computing, fully parallelized simulation possibility. And now we could allow even longer simulation times, even 1 hour, because within 1 hour you can solve full population, for example, for genetic algorithm in one go. Or then, even though it would take 1 or 2 hours, if you can get the full set of simulation in one go, you can easily run a proper optimization in a week. Then training AI, similar task, you need lots of simulations to train the algorithms and to have more accuracy for them. So with cloud computing and domain decomposition method we have available at Allsolve, this makes it possible to really reduce even the long optimization runs, and you can exploit it for 3D optimization as well. In superconductor field, this situation easily arises, for example, when considering fusion magnets, accelerator magnets, or cable design. With fusion magnets, such as tokamaks or stellarators, they are naturally very big assemblies, and if you want to, for example, consider even the full assembly with all the magnets, you can imagine how big the problem can be. For accelerator magnets, they are as well very big magnets with the ends, so that you cannot exploit the symmetries necessarily all the way, and depending the details, you can easily end up having a really large problems. And also for cable design. And then again, if you want to try optimizing properly, this is a big challenge, and Quanscient Allsolve is for tackling this. Next, I want to show you one example simulation we did last year. This is an example of a very large scale simulation, and we did a mesh sensitivity analysis for a full-scale stellarator magnet assembly. Here you can see the magnet assembly. You can see all the 30 coils. The shape is some very strange, so there's no easy way to exploit any symmetry there. And in this case, one of the coils were modeled as a cable accuracy. So in this one coil, we had all the 208 turns modeled. And then if you consider the approximate diameter of the stellarator, it's about 20 meters. You will get the picture about the size of the problem. And here on the bottom, you can see the mesh in the detailed coil. Also, there's the feature related to domain decomposition method, which makes the simulation so fast. We can divide actually the mesh in pieces and fully solve separate problems on different machines. And the different coloring here shows how the splitting was done. And this is fully automatically done, so user don't need to care about that. Yes, I want to emphasize this was made in collaboration with Proxima Fusion, and we presented the results last year in UCAS, and I won't go to the details, but you can see here the field solution, a magnetic field distribution in the full-sized stellarator, and there you can see the one detailed coil and the field plot on the coil, as well as the force density on the coil with all the 208 turns. And just to give you a picture about the size of the problem, in the largest simulation we did, it was for 317 million unknowns. And this was a static, magnetostatic problem. And with 500 nodes, so the problem was split in 500 pieces, fully solved separately, and it was less than 10 minutes we got the solution. And yes, next I can show how to put this one running. So I won't go to the details. This problem was fully set up by scripting, but you can do it as well graphically. And in next, Janne will show how to do that. And actually the setup Janne will show, it is really identical if you would, for example, if you would charge the detailed stellarator, non-insulated stellarator coil. And I will only show the simulation setting and how to put it running. So here you can see different simulations, and you can see as well, you can see the physics we are using, the solver, and the node count. So what you can do here, you can copy the project, we can rename it. And we can put it running. And to give you some more perspective, I will put another case running with less nodes. So there they are running. And since the problem is so large, it's difficult to visualize with all the element. It takes so long. So for that, I will make another copy with a more coarse mesh. And let's call it visualization. Now they are running fully parallel. And yes, this is all from my side at this point, and I will next give the talk to Jukka. And we can return to this after Janne's presentation, and we can see the results at the time.
Beautiful. Thank you, Mika. Now, already at this point, I'd actually like to inform everyone about our actually quite exclusive trial offer that we offer all of you guys here. So, put short, everyone watching here has the option for a free, and I mean completely free, no strings attached, 7-day trial with 50 core hours, and actually one of the very same geometry files used in one of today's demonstration. So, that will be the one with the 8 filaments embedded in a copper matrix Janne will demonstrate soon. So we have a landing page with a simple form to fill out asking only your work email and intended use case. Basically, what do you want to use the trial for if there is something specific you want to test out yourself. Simply fill that out, submit the form, and we'll send you an email within 1 business day containing your credentials you can use to sign in. And the same email will contain the geometry file you can import, but you can, of course, use any of your own files too. Again, as this is a cloud-based tool, there's 0 download. So right after receiving your credentials, you can simply head to allsolve.quansign.com, sign in, import your models, and start playing around with the tool. I'll actually paste the link to the chat right now, which you can, for example, open in a new tab and check out after the event. There we go. That out of the way, let's move to some GUI demonstration with some AC loss calculations. Go ahead, Janne.
Thanks, Jukka. Hello, everyone. I'm Janne Ruuskanen. I work as a senior solution specialist at Quansign. My background is in computational electromagnetics and applied superconductivity. Let's have a look at the slides. So, today's demo, I'm gonna show you how to simulate this kind of non-insulated HTS coil. So we have a stack of HTS tapes embedded into a steel body. And this research project is done in collaboration with Proxima Fusion. So I thank them for sharing the geometry and some of the results as well. So what we are going to set up on this geometry is a magnetoquasistatic formulation coupled with heat transfer. And next, in the following demonstration in the Allsolve GUI, we are going to go through the following steps. So first we create the geometry and the mesh, and then I'm going to show you how to set up the material properties for different material domains, how to set up the formulation for the magnetoquasistatics and heat transfer, and also how to set the sources, so the total net current source for the problem. And then we can have a look at how to set up the simulation and some post-processing. So let's jump into the Allsolve. So here I have already imported the geometry as a step file, and then I can do some additional geometries on top of it, like box or cylinder as done here. Then you have some basic Boolean operations that you can apply on your geometry. And here it's all built and setup. So we can go first couple of steps how to use the GUI on the geometry. Here you can hide some volumes if you wish. For example, here I just hid the air box around so that we can have a closer look at the actual coil design. So these two bars sticking out from the coil are the current leads, and then we have the HTS spiral going through the steel body. So the setuping simulation goes through 4 steps. As a first step that we just did is to set up the geometry. Then we can move on to defining our material properties, which we can import as a CSV files. Quite often we have like some parameters such as the copper resistivity as a function of temperature, for example. We have heat capacities, all that kind of stuff can be imported as a CSV file, or you can define your functions. Like we have here defined the current source ramp. So it's a ramp function going to 10 kiloamps so it's ramping up in this T ramp time, then it's gonna hold for T hold seconds, and then it's gonna ramp down in T ramp seconds. So all these kind of functions you can set up here with the shared expression property. Then let's have a look how to set up the different material properties. So here you have the plus button for the different materials. You have some predefined stuff like this YBCO material. Then you can select on which volumes you want to apply this material property. So here just clicking or clicking from the GUI, you can define the volumes. And then here appears the default material properties that are associated with the resistivity of the YBCO material. You have the typical N value, you have critical electric field value, JC, and the power law appear here that you can apply on the different material domains. Here I have defined copper for the current leads, steel for the steel body, and HTS for the HTS spiral. And then here you can define some additional shared regions for convenience for example, in the post-processing. For example, here I have defined cross sections from the spiral. So here I denote I spiral 1 as the surface, as the cross section surface of the HTS stack in the first turn, second turn, third turn. So these we are going to use, for example, in the post-processing. All right, so now we just went through the step 2, which was setting the material properties for the different domains. Now we can dive into setting up the formulation. So here from the Physics Plus button, you can choose the physics that you want to couple and simulate. Here I have chosen the magnetoquasistatics with H5 formulation. So here the H that is responsible, for example, for the current approximated with edge elements, that is defined on the conducting region where we have currents. And then the phi is defined in the non-conducting domain, so basically the air. That is the air box around the coil, and also in the center of the coil we have also some air material. And then how to constrain and source the problem. So for example, for the scalar potential phi, we want to gauge it, so we want to make it unique in the domain. So I fix it to 0 here at the outer boundary of the modeling domain. Then setting up the source, which is fully automized. I can demonstrate it here. So from the plus button, we apply current source. And we choose our terminal where we want to apply it. For example, here, I want certain current running through this terminal here. So we add curve, and then we apply the curve. Sometimes it's a little bit, my angle of view is a little bit tricky to select the curve, but it should be fine. So now with the right-hand rule, we see into which direction the current is flowing through the terminal surface. And now if we were interested in circuit coupling, so we can first of all choose if we just want to drive it with a known current or with the circuit coupling equation. So our input current was this function. We apply a total net current condition. So this is the total current running through the terminal equals to current flowing in the terminal voltage divided by some parallel resistor that is connected like in parallel with this coil. And this one I have predefined here in the shared expressions. So now with this equation, we are able to take into account possible external circuits that are coupled with our FEM model. Then, as I promised, we're gonna couple heat transfer, so thermodynamics, with this magnetoquasistatic formulation. So again, from the plus button, we add heat solid. We select the volumes where we want to apply that. And then we add a source or constraint. Here we apply Joule heating, which is the electric field strength times the current density in the very same domain. Yeah, that's pretty much about setting the formulation. It's pretty simple and intuitive. And now we can go setting up the simulation. So from the simulation plus button, we add a simulation. We set up the mesh. We have different options for setting up the mesh. You can use the default. You can use a little bit finer. You can also choose expert setting where you can make a denser mesh on certain areas if needed. And then you can see the preview on the generated mesh if that pleases you. then you're good to go. Or if you want to refine the mesh in certain areas, you can use the finer option here or go for the expert setting. Then you can set up some inputs for your problem, like some functions that we predefined. For the post-processing, you can set up some output fields, for example, like temperature field, magnetic flux density, current density, or you can also apply some custom expressions like AG. That is the Joule losses. You can integrate that over the HDS domain, for example. And the last argument is the integration order. So that's pretty simple, and then it will be calculated as a function of time. Then to run the simulation, we choose analysis type. That can be harmonic, multi-harmonic, transient. Here we choose the transient simulation. We choose the time stepper. Here we use implicit Euler. Start time, end time, time step size. Here you have options for direct solver or the iterative solver. Here we use the number of nodes. So here I will use 4 nodes, so it will split the mesh into 4 pieces and solve them in parallel using domain decomposition method. And then just hit the run button. And then it connects to the CPUs, the number of CPUs that you wanted to use, and then it will start to run. Here I have some pre-calculated results. For example, here in the beginning I mentioned the cross sections where I wanted to calculate the radial currents. The currents in the HDS spiral. Then we also set up the interpolating the magnetic flux density in the bore, so we see how it grows with the ramp. Tmax in HDS, so we can observe if the temperature goes too high in the simulation, or do we want to change some parameters in order to have a thermally safe design. Joule losses as a function of time are also plotted. And then for the post-processing fields, we can have a look how the temperature looks like when the heat is generated due to the Joule losses. Or we can have a look at the magnetic flux density, for example, in the geometry. This is plotted with vectors. Then we can have a look at the current density. So for example, here we see that typical for these non-insulated coils is that you can have a lot of radial currents during ramps. So here the radial currents are nicely visible. And then for the simulation, if you go to the logs section, you can see here how the time stepping is running. You see if it converges or not, and then there you can define some values that are also plotted during the time stepping, like the operation current and so on. Now it's at 7 kiloamps. All right, I think we pretty much went through the setting up this simulation for this non-insulated HTS coil. I thank again Proxima Fusion for letting us to share this geometry and some results related to that. So we can go back to the slides. And then a quick note about the demo project that will be shared for the trial use. It is this twisted superconductor filament cable or wire. And in the demo setup shared with you, with a slight difference to the just demonstrated one, we don't have heat transfer preset up there, but you can easily set it up and check if the temperature blows up or something. But yeah, other than that, it's a very similar setup as we just demonstrated with the coil. We can even have a quick look how it looks like in the Allsolve. So here again, the geometry was imported as a step file. You have an air cylinder around. Here you have the hide button if you want to investigate more the twisted filaments, for example. And here you would apply the material properties, like this is our air domain, this is our copper matrix, superconducting material. Next steps, setting up the physics, then simulation, transient, and so on. Okay, that's all from my side for now. Thank you very much, and I pass the ball to Jukka. Or should I say the buck?
Thank you, Janne. Very nice. So indeed, you'll get that step file if you sign up for the free trial, and we even have a tutorial video going over the detailed setup. So if you want to go do it with that, you can. If you want to import your own files, you can of course do that as well. But now for the next 5 minutes or so, before going back to the results from the stellarator simulations we initiated in the beginning, so one with 200 cores and the other with 500, let's cover some of the other benefits provided by cloud computing, more specifically Quansight Allsolve, since there are surprisingly many. We'll also touch on the pricing and maybe debunk some security myths. So to begin, the collaboration with a cloud-based tool is very straightforward for a couple of reasons. First of all, there are no user limits with our software. That means that when an organization purchases access to the tool, everyone in the organization can have access to the same project, no matter if you're a startup with 5 engineers or a tech giant with 5,000. So any bottlenecks caused by a limited number of licenses simply cease to exist. That also makes growing the user base within an organization very easy. Second, the kind of natural continuation of the first is that sharing a project with a colleague or superior even is quite literally as easy as sharing a link. So no more packaging and downloading files, no version incompatibilities with software, and no professional courtesy required while sending the file over through email. Now to briefly touch on the pricing. The exact pricing for a tool like this is, of course, almost always a custom one, fully depending on the needs of the company, the number of parallel cores required, and the number of core hours, etc. But what I can say is that the plans are extremely flexible and tailorable for the needs of both small startups with limited simulation needs, as well as to international conglomerates in need for a lot more. And as a multiphysics platform, all the features are always included, so there are never additional costs for any new use cases you might use the tool for. And as already established, there are no user limits, meaning that once an organization has purchased a plan, everyone can access the software even at the same time. Furthermore, as the pricing is usage-based, the quota only gets consumed when the simulations are running, meaning that with the sporadic nature of simulation work, there will never be expensive licenses sitting idle when there isn't a need to run the simulations. And when the simulation season is on, the number of licenses or computational capacity will never be a bottleneck. Something worth mentioning, by the way, is that actually most of our customers started using Allsolve as an add-on to their existing tool stack. So instead of outright replacing the industry giants from the get-go, they initially adopted Allsolve for solving the simulation that were simply not possible with their existing tools. In superconductors, it's exactly utilizing the possibility to run these giant third of a billion unknown simulations requiring up to tens of terabytes of RAM. And from there, many have realized that Allsolve can indeed handle all the rest too, and have then some slowly began discontinuing their expensive desktop-based licenses. Again, as everything is solved in the browser, you can solve these giant simulations with pretty much any machine with an internet connection. We have literally solved some on mobile phones. That means there are no hardware requirements or any cost associated with that. Onboarding new engineers, for example, is easier when they don't require any powerful workstations. And also, there are no cluster queues or any need to maintain those. So to reiterate, with the lightweight nature of the tool itself being entirely within the browser, combined with the usage-based pricing and absolute firepower when it comes to the simulations themselves, it's honestly no wonder that more and more companies working with superconductor simulations are starting to add also to their tool stack, if not outright replacing their existing software fully. Finally, let's address some of the most common concerns regarding security. Now, as opposed to the mainstream belief, utilizing a cloud-based solution might actually be more secure than using on-site machines. I'll explain my reasoning. So, mid-sized companies with annual recurring revenue from 100 million to 1 billion spend approximately 500,000 to 10 million annually on cybersecurity. Cloud providers like AWS, for example, that we use, even with conservative estimates, invest around 1.6 billion a year on cybersecurity alone. That allows them to employ top-tier security professionals, quite literally armed guards, and of course continuously update their security measures to stay up to date with the ever-evolving threats, and of course undergo rigorous security audits and certifications. So put simply, these cloud providers typically have more sophisticated and robust security measures than most businesses can afford to implement on their own, simply because their business quite literally depends on it. Anyways, with this now covered, with hopefully some new perspectives provided, let's go back to check out the results from our stellarator simulations. Back to you, Mika.
Okay, thank you, Jukka. We can go to the screen. And yes, you can see the simulation are still running, but we can check the logs now. With 500 nodes, you can see the partition of the mesh was done to 500 pieces. In this simulation, we also solved the orientation of the cables, so it takes some time, some milliseconds. And it was done in some pieces since we have different kinds of coil, one detailed and the other ones. So you can see the conversions of the orientation computation. Then we go to solving magnetostatics. And here you can see the number of unknowns. So here we have 317 million unknowns in the problem. And you can see the conversions the domain for the domain decomposition. So yeah, when we split the problem in pieces, they change data on the boundary of the problem, but otherwise they are fully separately solved. And you can see the conversions. We go down to 1e minus 8 tolerance. You can see the problem has been already solved. And then there's some post-processing and writing the data left. So that's actually may take longer than solving the actual problem. So this 317 million was solved in 500 seconds, so about 8 minutes. You can see also the 200 nodes running. It's also doing some writing the solution. It's also solved, and now with less than 800 seconds. So I hope this gives some perspective about the scaling of the problem. So with more nodes up to some point, you can really scale up a lot the speed, simulation speed. And with here with 250 and then compared to 500 nodes, there was about 300 seconds to scale down the simulation time. And you can imagine if you would use only one core machine. Then for the visualization, also it was solved in 70 seconds, but this was a way smaller problem with the coarse mesh. Let me find. So there was only 500,000 unknowns, and let's check the field plot, for example. So you can add the visualization as Janne showed, and I wrote the solution on the skin of the detailed coil. And let's see how does it look like on the browser. And meanwhile, when it's downloading the solution, I would really like to emphasize that for the setup Janne showed, it could be used as is basically for charging this kind of non-insulated coils. If this would be embedded in steel matrix, you can, if you have access to the current lead, you can, in the similar way, you can charge the coil. And in that case also, you don't need to take care any of the other constraints, because in non-insulated coil, you will have unconstrained currents due to topology of the problem. So you don't need to take care any of those. You can just apply the current where you want, and that's it. Everything is automatically handled. But yes, you can see the solution on this coarse mesh, and you can see here that we really have all the turns in the coil, and roughly on the skin the maximum is about 14 Tesla in this coil. Okay, this is pretty much this. Hope you got some picture about the cloud scaling and possibility for exploiting Quansa and Allsolve for big problems.
Beautiful. There we go. How nice is that? Now, before starting the Q&A in just a few seconds, I saw a couple of questions regarding the trial, so I could quickly do a recap of that. So basically, indeed, seven days, 53 core hours, and yes, we have the landing page that is linked right there in the chat, and yeah, it asks for business email, and some information on what you would like to achieve with the trial. So it can be something like just to play around with the GUI, see how the automated cuts work, or import your own models and test out the scripting interface. And after submitting the form, you will receive the credentials and the geometry file, and also the link to the tutorial, actually. And you can start simulating instantly after that. The offer is basically indefinite, good for now. But what we have, a sort of a more exclusive thing, is the evaluation package, which is well, normally we have this evaluation package of 3 months that it has 64 parallel cores that you can use to validate if Allsolve is really good for you or not. Includes 6,000 core hours and enough sessions with our experts to really not only get your projects going, but to also really get meaningful results as fast as possible. This evaluation package is normally 8,000 euros or so, but for you, our Superconductor webinar viewers, we are offering that for 40% off, so just a bit less than 4,900. And again, you can redeem that evaluation in the next 14 days, so a couple weeks from now. You can either start with the trial, see how that works for you, or either schedule a one-on-one time immediately. The link for that, for everything, is in the chat. Perfect. So I'll invite Mika and Janne here, and we can kick off the Q&A section. So if any questions have arisen, feel free to ask them. So just to make exactly sure, yes, you will be able to use the free trial later, although the current best offer on the evaluation package might have been expired then. And yeah, that's it. What do we think? One thing we can actually go and establish now, which many people often think about, is our connection to quantum, since our name is QuanScient. And if you follow us on LinkedIn, which I highly recommend you do, you will see a lot of posts regarding quantum. So basically, what we're doing is research on two fronts. So basically, we have this product QuanScient also that was just demoed, and then we are doing another branch of our company is doing research in quantum algorithms. So basically, how we can harness the power of quantum computers for multiphysics simulations. Currently, we're focusing on the CFD part for that, but the vision for the next couple of years is to slowly begin implementing these quantum algorithms to our existing cloud product. So that's the sort of quantum connection there. All right, there was a question, can you simulate active cooling?
So if by active cooling we mean some other kind of boundary conditions than we had in a demo, where we had actually adiabatic conditions, so no heat doesn't actually escape the coil domain. So yes, we can apply different boundary conditions like convection cooling, or if you wanted to go for more accurate simulations, you could couple that with different fluid dynamics, for example. Do you have, Mika, something to add to that?
That was yeah, basically no. Just that we have done as well some CFD simulations with cooling channels and heat transfer from the solid to the fluid, if this is what you meant, or
Yes, there was cooling using supercritical helium flowing through the conductor. Specified.
Yeah, basically, if this is a heat transfer from solid to fluids, we have done some simulations with some fluids earlier, and I think it's possible, yes.
All right, then there was another question. Can I check with the large stellarator example shown? Is that solving the static field with a known current distribution?
Yes, exactly. In that case, we applied homogeneous current, but if you want to charge such a coil, you can do it similarly as Janne showed. So we can solve a transient case for that as well, or with an other AV formulation, you can also solve such the current density as it would like to flow in the stack based on the resistivities defined. But the example that was done, it was with uniform current density in the stack.
Perfect. By the way, at this point, since the 60 minutes is up, I want to be respectful for everyone's time and just thank you. If you have to leave right now, thank you for participating here. We could continue just go through a couple of these questions now, but if you have to leave, then thank you for participating. There was a question from Emmanuel asking, can you walk us through the API usage of simulation for digital twin, for example?
The API, it's at the moment it's under work, and we have already done some testing with API interface, and it's coming soon. And then it's possible to, for example, exploit the optimization and fully write the scripting, which and then yes.
Right. Nathan asked, is the critical current density dependent on the temperature in the AC loss example?
So in the twisted filament wire example. I guess.
Yeah.
Do you, Mika, remember if there was a temperature dependence in the trial example?
In that case, it's only constant JC, but you can easily add any temperature dependence on that if you like. You can.
Yeah, in the shared expressions, you can write functions depending on different arguments.
In the spiral pancake example was specified.
In that one, we had JC depending on the temperature, norm of the magnetic flux density, and also on the orientation of the magnetic flux density.
Then for the final question, there was how the current distribution on the filament surfaces. So how would you interpret that? would that be applied on the filament surfaces, the current distributions?
Do you mean the AC loss example? If that case, yeah, it was distributed as according to power law, which is typically used for superconductors. So when you ramp up, the current starts entering towards the center of the filaments at JC, basically in that example. If you meant this.
Perfect. And just as a quick answer to Bernhard, yes, it is possible to get the recording, and each of the registrants will receive one in the next 24 to 48 hours. Yeah, with our time already ran out, we went a few minutes over time. Huge thanks to Mika and Janne for the answers and guiding us through the demonstration. And of course, a big thank you for our audience for participating and all the questions. Before ending, I'd quickly like to summarize what we just went through here. So again, if you are an engineer or in other ways dealing with superconductor simulations, you know that the setups can be complex and the runtimes can be very long. And what we wanted to show here is that cloud computing, so in practice, cloud-based simulation platforms, can be a viable, cost-efficient solution to not only solve this problem, but turn it into a strength. We saw a 3D nuclear stellarator simulation with more than 300 million unknowns being solved in less than 10 minutes, which I think serves as a testament to the message we wanted to give out. Now, for the final time, if what you saw here resonated with you and you want to get your hands on the tool or explore how Quants and Allsolve could expedite your workflow through a personal one-on-one call, in any case, please use the link that in the chat to fill out the form for the free trial or book a call for as soon as tomorrow if you're fast enough. That being said, thanks once again, everyone. We really hope today's session has provided you with the answers you came here for. Have a good one, y'all.